Here we are taking two random variables x and y. Okay, so we are just adding these two random variables, that is w is equal to x and y. Okay, so this type of principle will be getting in most of the practical applications where we are transmitting the original signal through the channel. When you transmit the original signal through the channel, what happens at the receiver side, we will be having the sum of original signal and noise as the output. Okay, so to solve such problems we are using this particular concept. Okay, so we'll be having the application where we are transmitting the signal in through the channel. Okay, so what is that here we are doing? We are taking two random variables x and y. Okay, so where x is the information, y is the noise signal. So if at the receiver, if you measure the signal, what happens? We will be having both information and noise. Okay, so what is w will be equal to x plus y. Okay, so for example, fx of x, capital Fx of x, and capital Fy of y. Capital F is used to represent distribution function, no? Or the distribution function of x and y. Then what is the probability distribution function of w can be written as Fw of w is equal to probability of w less than or equal to w. So what is w here? W is nothing but x plus y. So probability of x plus y less than or equal to w. So we are interested with the area where x plus y is less than or equal to w. Okay. Now we will be plotting this condition here in the xy plane. So what is that given? It is given that the information at the receiver, the signal at the receiver w will be equal to what? The information capital X plus the what is that noise y. Okay, so x plus y is equal to w. Now if you substitute y is equal to 0, we are getting x is equal to w on x axis. Similarly, if you substitute x is equal to 0, we are getting y is equal to w on y axis. Okay, so like that we will be getting y is equal to w on x axis, x is equal to w on y axis. Now if you join these 2 points, we are getting a line which is having the value y plus x plus w, x plus y is equal to w. Now if you observe this shaded part where x plus y value is less than or equal to w. This shaded part indicates the x plus y value less than or equal to w. Okay. Now what is that we are finding? We are finding the distribution function in the shaded area. So what is the distribution function? Fw of w. So here you observe this is not joint distribution, it is the marginal distribution. Okay, so Fw of w can be written as in the marginal distribution one of the variable. So you will be having two variables x and y. One of the variable will be having the value from minus infinity to plus infinity, whereas the other variable is having the value from minus infinity to x. Okay, otherwise you can take like this also, minus infinity to plus infinity, integral minus infinity to y also you can take. Okay, so you can use any of those two conditions. So in this case we have taken integral minus infinity to plus infinity, integral minus infinity to x, fxy of x comma y dx dy, like this we are taking. Okay, so from the definition we know that x plus y, what is x plus y is equal to w. Okay, so that is why we will be substituting what is x, x is equal to w minus y. Okay, so we are getting the fw of w, that is the probability distribution function, is given as integral minus infinity to plus infinity, integral minus infinity to w minus y, fxy of x comma y dx dy. Okay, this is the probability distribution function. Now how do you find out density function? Now here we have fxy of x comma y. No, see here in this equation we have fxy of x comma y. Okay, so in the beginning itself we have discussed that these two random variables are statistically independent. If the two random variables are statistically independent, then the joint density function will be equal to what? the product of individual density functions. Okay, that is fxy of x comma y is equal to fx of x into fy of y. We will be substituting same thing here. Now since these are independent, we are subwriting y integration separately and x integration separately. Okay, so this is fw of w. We got it as integral minus infinity to plus infinity fy of y integral minus infinity to w minus y fx of x dx dy. Okay, so this we got it. Okay, what is this? This is the distribution function. Now what is density function? Density function is derivative of distribution function. Okay, so we have to differentiate it. So it is d by d omega of f omega of omega will give us small f omega of omega. So we know that small f is what? Density function will be equal to differentiation of distribution function. Okay, so this differentiation we are solving by using Lebesgue rule. You have to use Lebesgue rule to solve this differentiation. Okay, so see here, this is the what is the using Lebesgue rule we are writing what is this differentiation. So this differentiation can be written as d by d omega of integral minus infinity to omega minus y fx of x dx can be written as fx of, substitute the upper limit omega minus y and differentiate this upper limit with respect to omega. So if you differentiate it with respect to omega, we got 1 minus substitute lower limit here. Okay, differentiate lower limit with respect to omega. Since lower limit is constant, differentiation of lower limit will be 0 plus integral minus infinity omega minus y partial differentiation of fx of x with respect to omega. Since partial differentiation of fx of x with respect to omega is equal to 0, so these two terms will be 0. So what is the result we get? We get fx of omega minus y. We'll be getting the result as fx of omega minus y. So this is the definition of Lebesgue rule we have written here. Just now we have discussed, no, same thing. So f omega of omega can be written as integral minus infinity to plus infinity fy of omega, and this differentiation we already discussed this, we have written as fx of omega minus y. So the differentiation is fx of omega minus y dy. Okay, so what is this? This is, and just now we have discussed, no, either you can take y limit as minus infinity to plus infinity or x limit as minus infinity to plus infinity. The other variable we have to take it as minus infinity to x or minus infinity to y. So if you are taking y limits as minus infinity to plus infinity, we will be getting this equation, ma. Okay, if you are taking y limits as minus infinity to plus infinity, we'll be getting this equation. If you take the x limits as minus infinity to plus infinity, here in the place of fy of y, we will be having fx of x. Here in the place of fy of omega minus y, we will be having fy of omega minus x dx. Okay, so we are getting these two equations. These two equations are nothing but the convolution integral of fx of x and fy of y. Okay, so that is why f omega of omega can be written as fx of x plus fy of y. Okay, like this we will be writing f omega of omega. So from this what we can say, the density function of sum of two statistically independent random variables, sum of two statistically independent random variables will be equal to what? It is the convolution of individual density functions. It is the convolution of individual density functions. Okay, so is equal to convolution of their individual density functions. Okay.